Assalamualaikum warahmatullahi wabarakatuh.
Perkenalkan,
saya Andika Eka Purnama,
saya Arnanda Wibawa,
dan saya Viona Octaviani Citra. Kami mahasiswa Institut Teknologi Telkom Purwokerto, Prodi S1 Teknik Telekomunikasi,
akan mempresentasikan tugas besar kinerja telekomunikasi dengan judul
OFDM pada sistem komunikasi satelit.
Ortogonal frekuensi diffusion multiplexing atau yang disebut dengan OFDM. Adapun topik yang akan kami bahas antara lain, pertama, apa itu OFDM? Yang kedua, bagaimana cara kerja dari OFDM? Yang ketiga, bagaimana penerapan dari OFDM? Dan yang terakhir adalah apa saja kelebihan dan kekurangan dari OFDM? Apa itu OFDM? OFDM atau Orthogonal Frequency Diffusion Multiplexing adalah sebuah teknik transmisi yang menggunakan beberapa buah frekuensi yang saling tegak lurus atau ortogonal. Selanjutnya akan dijelaskan oleh rekan saya bernama saudara Arnanda Satria Wibawa.
Sini saya akan meneruskan penjelasan dari saudari Viona. Sini ada sebuah blok diagram OFDM terdiri dari blok pada transmitter dan receiver, di mana pada transmitter terdiri dari blok-blok yaitu serial paralel, modulasi, IFFT, cyclic traffic, dan paralel to serial. Di blok serial terus paralel berfungsi untuk mengubah bit stream atau data input dari bentuk serial menjadi bentuk paralel. Setelah itu, data input tersebut akan diteruskan ke blok modulasi. Di blok ini, data yang menjadi rubah ke bentuk paralel akan dimodulasikan dengan modulasi BBSK, KAM, dan IPSK. Salah satu. Nah, di IFT ini merupakan blok terpenting dari OFDM karena IFT berfungsi untuk membangkitkan subcarrier dengan frekuensi yang berbeda dan saling overlap. Blok inilah yang bertanggung jawab mengenai hal tersebut. Blok ini juga mengubah sinyal dari domain frekuensi ke domain waktu, sehingga sinyal bit data yang dalam bentuk diskrit kemudian diubah menjadi domain waktu yang sifatnya kontinu. Setelah melalui blok IFFT, data input kemudian memasuki blok cyclic prefix, di mana pada blok ini berfungsi untuk mencegah terjadinya interferensi antar simbol. Simbol adalah istilah untuk setiap sinyal yang keluar dari IFFT. Jadi, misal ada 5 sinyal, maka sinyal keluaran IFFT juga ada 5 yang sudah memiliki frekuensi yang berbeda dan sudah dalam domain waktu yang acak. Sinyal inilah yang dinamakan simbol. Nah, untuk mencegah terjadinya interferensi antar simbol ketika kemudian sinyal-sinyal ini akan dikonvert kembali ke bentuk serial, maka diperlukan blok cyclic prefix, di mana blok ini memberikan sinyal tambahan di depan sinyal simbol sebagai tanda setiap simbol dan sebagai broadband pada saat dikonvert menjadi serial kembali. Selanjutnya, data input akan dikonvert lagi ke bentuk serial sebelum dikirim melalui kanal propagasi. Nah, di kanal propagasi itu sendiri ada noise, interferensi, dan lain-lain. Nah, setelah memasuki receiver, kembali seperti tadi, memasuki blok serial to input yang fungsinya untuk merubah data serial menjadi paralel. Kemudian pada blok remove cyclic prefix-nya dihapus. Kemudian pada blok FFT itu fungsinya kebalikannya dari IFFT. Begitu juga blok demodulasi. Dan untuk terakhir memasuki blok paralel to serial. Nah, di sini merupakan konsep OFDM, di mana yang atas merupakan konvensional multicarrier teknik. Jadi teknik multicarrier secara umum, sedangkan yang di bawah merupakan ortogonal multicarrier teknik. Nah, di sini dapat dilihat bahwa dengan OFDM kita dapat menghemat bandwidth. Di sini ada keterangan kita dengan metode OFDM dapat menghemat bandwidth sebanyak 50%. Nah, ini bagaimana OFDM bekerja. OFDM mengirimkan data lewat carrier yang terpisah pada frekuensi yang ketat. Jarak ini memberikan ortogonalitas pada carrier ini yang mencegah demodulator melihat frekuensi lain. Selanjutnya akan dilanjutkan oleh saudara Andika Eka Purnama.
Selanjutnya kelebihan OFDM. Yang pertama, efisien dalam pemakaian frekuensi. Yang kedua, tahan terhadap frekuensi selective fading. Karena setiap sinyal dalam OFDM saling overlapping satu sama lain. Jadi, ketika terjadi frekuensi selective fading, tidak akan terlalu mempengaruhi kondisi sinyal dan mudah untuk direkonstruksi sinyal pada sisi penerima. Yang ketiga, tidak sensitif terhadap sinyal bundar. Kecepatan transmisi yang rendah pada setiap subcarrier menjadi periodis simbol menjadi lebih panjang sehingga kesensitifan sistem terhadap delay. Delay spread menjadi relatif berkurang. Delay spread merupakan penyebaran sinyal-sinyal yang datang terlambat. Yang keempat, mengurangi ISI atau inter-symbol interference dan ICI atau inter-carrier interference yang biasa menjadi kendala pada saat transmisi. Yang kelima adalah channel equalization. Selanjutnya ada kelemahan dari OFDM, yaitu sensitif terhadap carrier frekuensi offset. Yang kedua, mudah terkontaminasi oleh distorsi non-linear karena susah untuk menentukan waktu start pada sisi FFT penerima. Yang ketiga, sulit untuk sinkronisasi sinyal. Sistem OFDM memiliki sensitivitas pada error frekuensi yang diakibatkan oleh perbedaan frekuensi pada penerima. Perbedaan ini diakibatkan karena adanya pergeseran frekuensi akibat efek Doppler atau efek pergeseran dan karena pengaruh ICI yang terjadi antara subcarrier. Frekuensi offset ini menyebabkan sinyal yang diterima tidak lagi ortogonal. Yang keempat, mengalami rugi daya akibat penambahan cyclic prefix. Teknologi OFDM sebuah sistem modulasi yang menggunakan multifrekuensi dan multi amplitudo sehingga sistem ini mudah terkontaminasi oleh distorsi nonlinear yang terjadi pada amplifier dari daya transmisi. Yang kelima, PAPR atau peak to average power ratio yang tinggi, yaitu merupakan perbandingan antara daya puncak dengan daya rata-rata yang diterima. Terima kasih.
Hello friends, today, how can we stream a full HD movie seamlessly, which seemed impossible in legacy networks? So friends, in this video we have shown what are the limitations of wireless channel, how wideband single channel are inefficient for transmission. To overcome, how wideband single channel is divided into small subcarriers and increase efficiency by reducing delay spread. How concept of orthogonality is introduced in FDMA and achieved multifold throughput. Hi everyone, welcome back to the world of 4G.
Previously we have shown how mobility and global connectivity was achieved by introduction of wireless communication. But there are several complexities associated with wireless channels. Multipath fading. Unlike a wired channel, which uses a fixed path, the signals in a wireless channel can reach a user using multiple paths. All these signals known as multipath components may have different channel gain and time delay. This combined effect causes what we know as multipath fading. Delay spread. As a consequence of multipath propagation, the duration of a symbol gets extended. This may interfere with the next symbol. This is called inter-symbol interference or crosstalk. Guard periods are introduced to avoid crosstalk. Frequency selective fading. Signals having bandwidth higher than the coherence bandwidth of the channel faces variable attenuation at different frequencies. This ultimately distorts the signal, and giving rise to frequency selective fading. Complex channel equalization techniques are employed to reduce it. Inter-channel interference. Often signal bandwidth of adjacent carrier frequencies overlap with each other, giving rise to inter-channel interference. Guard bands were introduced to avoid inter-channel interference. All these limitations compounded with the scarcity of bandwidth, gave rise to multiple access technique, OFDMA. Before diving into OFDMA, let us understand multi-carrier wireless transmission system.
Suppose a signal is to be transmitted over a bandwidth B, and carrier frequency FC. Then symbol time for this would be TS equal to 1 by B. For a single carrier wideband channel of let's say 1 MHz, the symbol time will be 1 microsecond. Given that the delay spread of the channel is of 2 microseconds, the combined symbol time would be 3 microseconds. Which means delay spread occupies 66% of the combined symbol time, thus reducing the efficiency of the channel by 1/3. As delay spread is difficult to control, the effect of delay spread can be minimized by using multiple subcarriers of lesser bandwidth. So instead of having a single carrier of 1 MHz, we divide it into 100 subcarriers of 10 kHz. Each having a symbol duration of 100 microseconds. So a delay spread of 2 microseconds will have a negligible effect over the channel efficiency. This concept is used in FDMA, which uses slowly modulating subcarriers of higher symbol duration. As these subcarriers are modulated with data, they gain bandwidth centered around the subcarrier's frequencies. Guard bands are used to separate them in frequency domain. We can represent this transmitted signal in the equation form as shown here, where summation of individual symbol multiplied with different carrier frequencies and transmitted at radio frequencies. OFDMA or orthogonal frequency division multiple access is a special case of FDMA, where users are provided a set of subcarriers overlapping in frequency domain. However, these subcarriers are specially designed to be orthogonal to each other, which allows them to occupy the same bandwidth without any interference. This in turn negates the use of guard bands. As a result, the subcarriers can be closely packed to increase channel efficiency. Now, before looking at the multiple access part, let's understand how OFDM or orthogonal frequency division multiplexing works, and how it's used in long-term evolution.
In OFDM, high-speed data streams of large bandwidth are split into parallel, slower substreams of lower bandwidth called subcarriers. These subcarriers are centered around frequencies in multiples of 15 kHz on both sides of DC. As the lowest subcarrier is of 15 kHz, symbol duration TS is equal to 1 by 15 kHz or 66.7 microseconds. Consequently, a one subcarrier can provide a symbol rate of 15 kilosymbol per second, which is analogous to having a symbol rate of 1 symbol per second for 1 Hz of bandwidth or half the Nyquist rate. Unlike in GSM or UMTS, LTE supports variable bandwidth as shown in the table. As the bandwidth increases, so does the number of subcarriers in it. Let's take for example, LTE bandwidth of 20 MHz, which has 1,200 subcarriers and thus a subcarrier bandwidth of 18 MHz. 2 MHz used as guard band. Here we have 600 subcarriers on both sides of the DC frequency. All these carrier frequencies are harmonics of 15 kHz, varying from -9 MHz to 9 MHz. In time domain, these subcarriers will be represented as everlasting sinusoids at these carrier frequencies as shown. However, in order to transmit data over these subcarriers, they are loaded with modulation symbols that represent the constellation points of digital modulation schemes, like UPSK and nth order comms. Also, the symbol duration for each of these subcarriers is always equal to 66.7 microseconds, which means that all these subcarriers have a whole number of cycles in one symbol duration. As we know that a rectangular function can be represented in frequency domain as a sinc function which is centered around DC. When multiplying a signal to a carrier frequency in time domain, signal will be shifts in frequency domain by the same amount of carrier frequency.
Thus we can represent these modulated subcarriers in frequency domain as a series of sync waves centered around the carrier frequencies. Basically, we are having 1,200 such sync waves. There are 2 points to be noted here. Firstly, the subcarriers are overlapping in frequency domain. As we can see, the subcarriers are placed in a manner that all the other subcarriers have a zero component at the peak of one subcarrier. Such subcarriers are called orthogonal. As a result, a mobile can sample the frequency and phase, without any interference from neighboring subcarriers. Orthogonality is achieved by ensuring that all the subcarriers have same symbol duration Ts, and the subcarrier spacing is maintained at delta F equal to 1 by Ts. Secondly, presence of negative frequencies. It can be explained by the fact that the subcarriers are transmitted below the radio carrier. So friends, today we learned how information is split into smaller subcarriers in multi-carrier modulation, and how efficiency was increased by placing them orthogonally. In our next video we will show how data starts its journey as a stream of bits and are finally transmitted as radio signal. So friends, don't forget to subscribe to our channel, like our videos and comments your views or suggestions. Happy learning! Streams of data, in the form of bits reaches network gateway from various sources. The gateway forwards it to the E node B, but how does the E node B converts them into radio signals and transmit them to the user over the air interface? How does the user equipment communicate back with the node B? Hello friends. Welcome back to the world of 4G. Today we will discuss uplink and downlink data transmission in the network.
As discussed earlier, data is transmitted in OFDM over parallel subcarriers of 15 kHz. The subcarriers are further divided on the time axis as blocks of one symbol duration, or 66.7 microseconds. This basic unit is known as resource element. Each resource element carries one symbol. Now, in order to transmit data over these resource elements, first data is modulated with specific modulation scheme. This scheme depends on the physical channels mapped on the resource grid. Suppose we have 8 bits of data to be transmitted using QPSK modulation. The data will be divided into 4 parallel streams of 2 bits. Phase and amplitude assignment is done according to the QPSK constellation. Finally, data is placed over the resource elements by adjusting the phase and amplitude of subcarrier to those derived for the data stream. Mathematically, it means multiplying the complex modulation symbol to the corresponding subcarrier frequency. Thus, in a 20 MHz channel, all the 1200 resource elements carrying 1200 symbols over 1200 subcarriers are modulated with appropriate modulation scheme. Now, since the data is modulated over 1200 subcarriers, a transmitter will require 1200 oscillators for its generation, and another 1200 will be required by the receiver for proper demodulation. The hardware complexity and sheer amount of power consumption would have left OFDM to theoretical idea and far from implementation. OFDM was made reality with the advent of digital signal processing techniques. So, instead of using 1200 oscillators, IFFT solves this problem by converting the parallel frequency domain signals into samples of a composite time domain signal, which are much easier to generate at transmitter side. All we need to do is to send these time domain samples at radio frequencies. As the data is being sampled by IFFT, samples must be taken above the Nyquist rate for faithful reproduction at the receiver. For an LTE spectrum of 20 MHz, the highest frequency component is 9 MHz, which means the sampling rate should be greater than 18 megasamples per second. In other words, 1200 samples per OFDM symbol of 66.7 microseconds. Since UMTS had a sampling rate of 3.84 megasamples per second. To achieve backwards compatibility, sampling rate in LTE is taken as multiple of 3.84 megasamples per second. Thus for 20 MHz spectrum which has a sampling rate of 30.72 megasamples per second, there are 2048 samples per symbol in OFDM-A. The FFT size of the IFFT processor thus depends on the LTE bandwidth as shown.
Now, previously we have shown, in wireless channel due to multipath propagation, we face delay spread and inter-symbol interference. We have also discussed how its effect can be reduced by increasing the symbol duration. Also, how guard period were used to eliminate it. But abrupt changes in time domain during transition period, from symbol to guard period causes inter-carrier interference in frequency domain, and disturbs the orthogonality between subcarriers. So in OFDMA, we employ a more complex kind of guard period, called cyclic prefix, in which end part of a symbol is transmitted in the preceding guard period. It also ensures orthogonality between the subcarriers, by keeping the OFDM symbol periodic over the extended symbol duration and therefore, avoiding intercarrier and inter-channel interference simultaneously. Since OFDMA uses composite IFFT samples, cyclic prefix is added by taking some samples from the end of a symbol period, and placing them at the beginning.
Now this time-sampled signal is converted into analog wave by a digital to analog converter. Further composite waveform is modulated at the desired radio frequency for transmission. For an example, an operator having license for 2320 MHz to 2340 MHz. The 18 MHz band will be mapped from 2321 MHz to 2339 MHz using analog modulation. And finally the A node B transmits signal over air. In node B, informs the user about the allocated subcarriers and the corresponding modulation scheme. So, when the RF signal reaches at the user's terminal, all these processes are reversed and finally user is able to receive the data intended for it.
Although there are many positives in OFDMA, but IFFT summation of multiple parallel subcarrier results in high peak to average power ratio. High PAPR results in high power consumption for signal generation, but handheld devices have limited power capacity. This makes OFDMA unfavorable for uplink transmission. In order to overcome this, LTE uses SCFDMA in uplink direction. In OFDMA, we have one-to-one mapping between symbol and subcarrier, but SCFDMA allows a symbol to be transmitted in parts over multiple subcarriers. For example, in OFDMA one symbol occupies one subcarrier of 15 kHz, but in SCFDMA, same symbol is distributed among multiple subcarriers of 15 kHz. In short, SCFDMA behaves like a single carrier system with short symbol duration compared to OFDMA. To achieve this, SCFDMA introduces the endpoint FFT block right after the serial to parallel converter in the OFDMA structure. The FFT block converts parallel sequence of symbols in time domain to different frequency points. Now, peak to average power ratio is proportional to the square of number of carriers involved. SCFDMA reduces PAPR by reducing the number of carriers. Obviously, there are problems in single carrier transmission as we discussed earlier, but the side effects are reduced by ensuring that the total bandwidth over which a symbol is transmitted is still not too high. Apart from this, remaining block in the uplink direction is same as used in downlink direction.
In our next video, we will be talking about physical, transport and logical channels used in long-term evolution. So friends, don't forget to subscribe to our channel, like our videos and comments, reviews or suggestions.
Sekian pembahasan mengenai OFDM pada sistem komunikasi satelit dari kami. Untuk kurang lebihnya kami mohon maaf. Wassalamualaikum warahmatullahi wabarakatuh.